Just a minute, sir. We'll introduce you to the audience, then we can start, sir. Loganathan. Just a minute.
Yes, sir. Okay, sir. Okay. I'm just checking whether the slides are
Hello?
to see.
Yes,
Yeah,
slides are moving. Sir.
Hello.
Yes, please.
Sir, this is Dr. M. Prasad, Associate Professor, Department of CSE, SVCW, Bhimavaram.
Before introducing, please keep his slides, sir. So that yes, now we can proceed, please, sir. Proceed, sir. Prasad, please introduce.
Yes, it gives me great pleasure to introduce Dr. Loganathan Veeramuthu. So, Dr. Loganathan Veeramuthu is presently working as a research assistant professor, Institute of Organic and Polymeric Materials, National Taipei University of Technology, Taiwan. He has vast experience in academic and research. He awarded with a PhD degree by National Taipei University of Technology in the year of 2021. He attended more than 50 webinars during the pandemic time. He presented his research work in various national and international conferences. His work is not only published in various reputed journals but also published as a book chapters by reputed publishers. He attended a bunch of FDP programs conducted by the reputed organizations. Dr. Loganathan Veeramuthu got more than 15 certificates from various reputed research academies. He delivered his research talk in various FDPs, STTPs, and national and international conferences as a keynote speaker. So he won quality award in the years of 2018 and 19 also from National Taipei University of Technology, Taiwan. He won Taiwan's prestigious research scholarship award from CTCIF Foundation in the month of December 2020. His research fields are electrospun nanofiber technology, wearable electronics, smart textiles, pro servostick, and optoelectronic devices. He likes people to share the knowledge and work in collaborative manner. Sir, we are really glad to have a resource person like you, sir. Now I request you to share the knowledge on the very emerging area like convergence of nano microstructure sensors and IoT. Thank you very much, sir. Please continue your topic, sir.
Yes, thanks for the beautiful introduction from the team, organizing team, Professor Prasad and Professor Kiran sir, who give me the opportunity to present to the audience. Yeah, I'd like to share my screen now. Yeah, please. Yeah, I feel it's okay, right? Or I can make it full screen like this. Is this okay? Now it's fine.
Yes, it is nice. Now, please proceed, sir. This is good.
Yes, yeah. Okay. So yeah, good afternoon, good evening, one and all present here. Today, myself, Loganathan Veeramuthu, and my topic is about convergence of nano microstructured sensors and Internet of Things. Because this FDP is focused on artificial intelligence and cyber security. Now I have an opportunity to share about sensing, because sensors are the basic components which is going to be influential factor for all these things. So first we should know about sensors, then only we'll compile everything together and form this kind of interesting field. So first we'll introduce about sensors. Now first, before going into the topic, I want to introduce a little bit about Taiwan. So this is the Taiwan map. Here you can see. I think I can use the laser pointer here. Okay. Yeah. So now you can see this is the Taiwan here. Here on the northmost part, this is the capital, Taipei, and this is one of the tallest building. Yeah, in Taiwan. This has 101 floors, 101 floors. So this one is shortly termed as 101 building. And this is my university. Here you can see my university. the Taipei Tech, shortly known as Taipei Tech, and NTUT, National Taipei University of Technology. This is the main entrance. And I'm working under Institute of Organic and Polymeric Materials. And my specialization is wearable devices and some optoelectronic wearables. Yeah. So now we'll get into the topic. Sorry. Okay. Yeah. In the initial conventional stage, we always depend on wearables, means it eventually comes to our mind that, yeah, what we rely on. First of all, how the human society has evolved, how they build this kind of wearable cloths. For example, they start with some plant-based materials and then they emerge slowly. They know how to weave and handloom those things, and they can form a beautiful fabrics like this. And they also use some animal-based sources like yeah, wool, leather, because they want to process these hides and they make leather. And because of this kind of processing, they also have some harmful effects to the environment. So we are also working on some sustainable methodology where we can eliminate this kind of environmental toxicity. So that is another field. So now I'd like to introduce about the wearables. So I want to focus on this kind of garments. We know that garments are different varieties. From here you can see air permeable. For example, if you want to wear the garment, wearable things, it should be easy to breathe. So you can you feel very cool, or if you want to feel warm, you have to prepare some thermal management like that, or you want to manage your moisture. For example, if you are working out and your moisture, for example, if you are going to sweat, then you should go out, right? So that you can feel comfortable. So these kind of things are very important for the wearable devices as well, not only for the cloths, because it's going to be integrated into our body or on our body. So yeah, these are all the important things. And in the recent years, we also face many pandemic situation right now. So we also focus on something like non-woven structures like this. Here you can see these are all called non-woven structure. It's not a woven structure. It is irregular, non-woven, so that it can filter small particles. So that is different field. They work on something like it will be helpful for your mask application, something like this. So now I want to focus on Internet of Things, right? So first of all, what is the basic component to, yeah, integrate into your device? If you want to fabricate a device, that device should be able to sense your body motions, or it should sense your something like what you are interested in. For example, if you want to sense your body temperature, or if you want to monitor your environmental toxicity, like for example, if you want to sense your metal ions or any other toxicants or biomolecules. For example, if you want to monitor your glucose level, how will you monitor? So these are all the factors we are looking upon. So for the sensing, you should have some analyte like this. So if you have your target analyte, your analyte should be very specific to your device. If it is, for example, if you want to measure the glucose level, it should only measure the glucose level. It should not interfere. For example, other factors like, for example, your temperature or humidity, if it is going to interfere, then it's of no use. So you should create some selective sensors so that it can be working good. Or the sensors can be multifunctional, but it should not interfere with each other. So that is more important. And in this case, in the right situation, we are working on many Internet of Things, right? So why we want Internet of Things? Because all the presenters before, they introduced everything in detail. So I don't want to go more details into this. So I can just show the important things, what is happening with the Internet of Things. It is applied in many fields like technology, transport, agriculture, smart cities, and security system, energy generation, like these kind of things, and for remote health cares like that. So if you have any health issues, how can you rectify yourself, especially during this pandemic period, right? So if you have some health discomforts, how can you track yours? So you should have some wearable device. It can be integrated into your body or onto your body. So you can easily monitor your health levels. For example, if you're going to working out, because in the real time, we have many wearable devices, it is getting commercialized as well. For example, iWatch, Fitbit, many things like this, right? So yeah, now the people working on this kind of field are able to get some real-time applications and it is working, right? So now wearable sensors present scenario. So in the current stage, these are all the things we are able to see. Not only for wearable means not only for your implantable. You can also implant this kind of device into your body so that it can sense all the necessary analytes you want to measure or what you're interested in, right? So yeah, other things apart from sensing, it is also helpful because in order to make your sensors to work, you should have some energy system. You should provide some energy because the sensor system works on the power input, right? You need some power input. So people also work on energy storage devices so that they can easily integrate energy storage devices. With the help of the energy storage devices, they can give the power to your sensory device so that you can keep tracking your performances. Now, in this case, you can see there are many inorganic conductive fillers. Why we want to rely on something like inorganic conductive fillers? Because I hope everyone is not from this science background, because they are from different backgrounds, right? So I can just give some small example. For example, if you want to pass your electricity, what factor you have to think first? If you want to pass voltage to work your device, then you should have some conductive system, because in our high school or junior high school, everyone might have studied what is the importance of conductors, because the conductors is going to conduct your electricity. It's going to allow the electrons to flow through so that you can have the device to work. For example, every device, whatever the sensors or something like optoelectronics, you need the basic component called electrode, which should be conductive. So the major criteria to fabricate the device, the essential part is your electrodes. It should be more conductive and it should be robust. Robust means it should work under wearable conditions. If you are going to walk, your muscles is going to stretch or flex. So under that strained conditions, it should work without any interruptions. That is more important for your device performance. And there are many different strategies to achieve a good wearable device by structuring your sensors. For example, our topic is nano and micro structured sensor. So we need to engineer our sensor structures. So if you can engineer your structures like this, for example, you can see here serpentine like a snake. You can see, and this one is bridged islands and kirigami patterning or liquid metal infills, mogul patterns are like this. This is the pattern which I propose in my work, so I can introduce you in the upcoming slides. So these are all the different kind of micro and nano structured sensors, which is going to alleviate the stress which is created when we are going to work out. So yeah, this is more important. And now I can show you this thing here. They are highlighting many different energy sources like solar energy, thermal energy, mechanical energy, because I'm speaking about wearable devices. So essentially, our body is going to move every day. Biomechanical motions, it's ubiquitous. It's everywhere. So if your body is going to move, means you can harvest the energy from there itself, right? Or if your body temperature can be harvested, then it is good. Or if you're going to use some electromagnetic, for example, if you're working on the computer, it has some electromagnetic radiation. So that kind of electromagnetic radiation can be converted into energy. That there are many generators. That is what mentioned here. You can see piezoelectric generators, triboelectric, electromagnetic generators. There are many generators, right? So I can introduce a little bit about it. Okay. So now, first of all, I should start with this because the sensors usually work on this basis. Like T and G is nothing but triboelectric generators, and P and G is piezoelectric generators, and some solar cells or this kind of, these are going to generate the energy. And now, if you are integrating into your fiber system, or for example in your textiles, then you can harvest the energy, right? Then that energy can, because it's going to convert your biomechanical motion into electrical signals in the form of waves. So that waves can be easily transmitted using Internet of Things, using our 6G, 5G communication. So you can easily wirelessly transform all your details. For example, if you want to monitor your health, then you can easily monitor your body motions or heartbeat, all these kind of things you can monitor by using this kind of sensory systems. So this is another schematic. Here you can see what are all the factors we can monitor, like physical signals, pressure, motion, tactile, vibration. This kind of things can be monitored using this kind of wearable sensors, and smart textile, smart watch, smart band, thermometers, because you want to monitor your body heat or something like if you want to study your cardiac motions or muscle movements, brain waves. So that are all possible using this kind of wearable sensors. Then we can connect with the wireless communication with this kind of devices. Then we can easily diagnose our diseases, or if you have some discomforts, or if you want to contact your medical practitioner, you can easily connect with them using this kind of IoT system. So it's very useful, right? So now I also want to introduce something like implantable devices. Here you can see they are using this kind of devices into the mice, and then they are going to study their physical motions or what kind of effects they are going to have. If they want to monitor some medicinal effects, if they are going to inject some medicine, for example, if they want to monitor their cancer level or something, like if they want to check their wound healing properties, that kind of things they can easily monitor by using specific sensors. So not only wearable sensors, we are also focusing on something like wearable photonics. Why we want this kind of photonics as well? Because if you're going to work out and you want to monitor by using this kind of platforms, using some 6G, 5G techniques, and then you are going to transmit all your data to there, and then it's going to be displayed into your smartphones or your laptops, right? So now, if you want to avoid this kind of things, you can directly get your device performance into your handheld devices. So you don't want all this kind of communication system. You can directly monitor by using this kind of wearable photonics. So that is also important. So not only wearable sensors, wearable photonics also very important for the upcoming days. So yeah. And if you have some elder people in your home, you want to monitor them. If you want to monitor the health from remote locations, then you can easily monitor using IoTs. So another factor is you can also create some self-powered nerve simulation system. Here you can see they are using some kind of self-powered, because in this case you don't want to provide the energy, because that is one of the drawback. If you are running out of energy, then you cannot monitor yourself. So if you have this kind of self-powered system, you don't want to rely on any power source like capacitor or battery system. So this is more important. So this is quite interesting. So we are also doing this kind of self-powered devices. And here you can see there are many methods to prepare some conductive polymer electrodes, because in the beginning I said for preparing the sensory devices, the major thing is your conductive polymers, conductive electrodes. Then there are many different conductive materials we might have aware of. So usually we are using copper, silver, gold, this kind of conductive materials. Apart from that, there are many polymer based semiconducting materials. So that can also be used as your conducting materials in your wearable devices. So these are all the examples. Yeah, you can just go through if you are interested in this. And then now I want to introduce about something like functional materials, because not only your conducting material is going to be helpful for your devices, you need some functional materials that should be very specific to your needs. So this is a small example for the functional material called perovskites. Perovskites is like a natural material, mineral based material. You can process it because it has many exciting features. For example, if you are looking upon some solar cells in the recent few decades, many people focusing on perovskites because it has very good efficiency, but the problem is their stability. Their stability is low, so you cannot use it for a long time. So that is the major drawback of this material. So I can go into other details. For example, here, this is the perovskite structure. You are seeing it, and it has ABX3 type. Here, this is the precursor. Here you can see CSBR is nothing but some, you can consider this as one precursor, and this is one more precursor. If you are going to mix and process it, you will be ending up with different kind of perovskites like 0D, 3D, 2D perovskites. If you are able to tune their morphology and their structures, then you can get some exciting results. So depending on the structure, work function, this kind of details, if you tune, then you can apply it in specific applications for solar cell, LEDs, thermoelectric, space electric, artificial synapse. There are many different applications. So perovskites are quite interesting material. It has different properties. And now, mm, Okay. Yeah, I'm able to. Okay. Now, I want to introduce another material called MXine. This is another material. Before I introduce you, that one is called perovskite. This is another functional material called MXine. This is like two layered structure. You can see they are layered. Here you can see what is the difference here. They are 3D structure. If you can etch this kind of here, this is the zoom view. Here you can see the aluminum layer here, the gray one. If you are able to etch this kind of aluminum layer, then you will end up with some 2D materials like this. 2D materials have their exciting features, like they have very good sensing capability, energy harvesting, catalysis, EMI shielding, biomedical application, energy storage. So this is another functional material. The other one is this one. Everyone might have heard about for the past few decades, because graphene is conquering the entire research, because it's very cheap, and they can before it was not cheap, because we are trying to use them. We synthesize with mechanical exploration. So apart from that, they now emerged into different using different techniques. They can process GQDs, especially not graphene or graphene oxide. Now they make graphene quantum dots, which is very small quantum structures. So this kind of quantum structures can give very good optical properties, and as well as something like sensing properties as well. So there are different methods like solvothermal, or something like laser induced graphenes, or something like ultrasonication, probe sonication, microplasma treatment, microwave methods. There are many different methods to prepare this kind of graphene quantum dots. So if you are interested in, you can check all these publications. And then I'd like to change my slide, but it's not moving. Sorry. Okay. Yeah. Now I want to stress why we want this kind of wearable sensors and self-powered sensors, because in the past, what we are using is we always rely on some energy sources. That energy sources are non-renewable sources. So we need some renewable energy, especially like this kind of wearable self-powered devices, which is going to reduce your energy consumption into your day-to-day life. So that can contribute to some good uh, outcomes. For example, our carbon emission is getting higher and higher day to day. So how to reduce the carbon emission? Just by using some green strategy like hydrogen fuel or some. There are many different ways, but now many people focus on energy storage system, lithium ion battery to store the energy. But anyway, the energy are getting generated from non-renewable sources, so that is not that good. So yeah, the future will turn out to be a different way. So yeah, we hope that we will get some exciting results in the upcoming days. And then why we want this kind of wearable self-powered devices, and what kind of factors are very important for your wearable sensors. For example, it should be lightweight, size should be smaller, and it should be washable, and it should be heat resistive, connectivity should be good, and it should work durable, and the sensation, functionality, multifunctionality. These are all the things very important for the wearable sensors. And then these are all the energy contribution, and energy crisis is getting higher and higher day by day. And wearable electronics, the market trend is getting higher, because everyone want this kind of IoT based system, because they can easily track their records, and it's very transparent, and you can keep tracking all your details easily in one touch, right? So other one is, I want to introduce something like fibrous electronics. Here you can see there are different strategies they are using to prepare. Here you can see this is like conventional spinning system. They are using core shell structures, and the other one they are using some spacer fabric, and that is going to act as your sensing unit, because they are using this kind of 3D spacers, and they use some dielectric layers in between. So if you are going to apply some pressure, then you can sense, because here you can see the capacitance. I'll introduce those things, the fundamental things about what is called capacitance and how they vary upon some stress or strain, those kind of things. And this is another method. They are using elastic yarn, commercial yarn, and then this is wet spinning method. In this, they'll use some polymer and some functional materials inside, or conductive materials, to fabricate some conductive electrodes. And here you can see, if you want to monitor your strain, body strain, then you have to prepare something like conductive electrodes like this stretchable one. If you're going to stretch, if you're going to work out, your muscle is going to stretch. That time it will create some crevices like this. This kind of crevices means your resistance will go higher, because the conductivity and resistance is not directly proportional, it's inversely proportional. So upon different strains, the resistance will go up and up. So depending on your strain percentage, your resistance will vary. So using delta R by R, the resistance change divided by initial value, then you can easily monitor your body motions. And the other one is they are also using some IPL irradiation to fuse. This is to fuse two different layers. For example, here you can see this is like a hexagonal structure. This is one material and this one is nanoparticle. They are fusing this by using this kind of irradiation, like welding, how we weld two different contacts, right? The same way they are nano structures. They are going to weld them by using some irradiation, by some rays, right? So after sintering, they'll form a percolative structure. The electron can easily flow through. That means your conductivity is good. So upon straining if you're going to work out on this kind of materials, you are going to use this material on your body. And if you're going to apply some stress, that time the resistance will vary upon your different kind of stress. So in this article, you can see they are showing how much percentage the strain is getting created when you are using different body motions. For example, your elbow motions or your finger motions or face muscle motions, hand motions, wrist motions, what kind of percentage, what kind of strain percentage will achieve. So they give some approximate values. Then here, yeah, the recent strain, you can see the basic watches and smart watches growth is getting very high, and wristbands, clothing, smart clothing in the recent years, it's getting higher and higher. And this one is to highlight wearable electronics growth. The recent publications in the last few years, you can see it's growing a lot. And then nano generators to get some energy with your wearable electronics as well. So this is quite hot topic to discuss with. And the present scenario, and this is work we done in our lab. And here we are using some wearable optoelectronics. Here you can see we are using some stretchable polymer based perovskite LEDs. And then this is another article we published recently. This is self-healable polymer. Even after cutting, it can heal by itself. And then it's mechanically robust. You can see initially it was like this, and after getting healed, it can be bent and it can be twisted, and which is having very good mechanical properties as well. So yeah, and then we apply this kind of emissive materials into light systems to prepare some optoelectronic system which is quite robust, and then which can be reused. Because if you're not going to heal your material, for example, you are going to use your electronics, for example, if you are using your mouse and the mouse is having some problem and you cannot recycle it, the recycling rate is very less. So if you have some problem, you want to repair it, or it can repair by itself, means it's quite good, right? So self-healing is like that. It can heal by itself. So you are not going to lose its functionality. For example, if you have your phone and its screen is got torn by like that, or if it get broken or if it get cracked, it can reheal. It can heal by itself. So it's good. So you don't want to replace them. The electronic components can be healed by itself, means that's good. That is quite good, and economically it's favorable. So it's interesting. So yeah, in future we can see a lot of self-healable materials. And the problem is the balance of self-healing time as well as your mechanical strength. It's quite challenging, so people work on those things. And here we can see there are many biomedical applications to monitor your blood oxygen saturation level, blood glucose level, heart rate, blood pressure. This kind of things can also be monitored with wearable sensors. And now I'm going to introduce different structures. For example, buckling structure, microbelts, serpentine, Holy structure, nanomesh structures, kirigami patternings. We used to play when we are kids to make some stretchable components by cutting, right? That is very simple to make. Here you can see how it works. This is a simple way to make some stretchable electronics like this. And then here, I want to introduce, because I work on fiber-based light emitting systems as well as some sensors. So I want to introduce, there are different methodology to prepare 1D material, fibrous material. So starting from melt blowing, centrifugal or force spinning, and then blow spinning, laser assisted melt blowing, microfluidic electrospinning. So this is melt spinning. Here we'll put the polymer and we just melt up to its melting temperature, and then we extrude them, and then we can collect as a fiber like this. And this one, centrifugal or force spinning, it's similar like our cotton candy maker. Here we will put our polymer in the middle, and then we pass some air, and then we rotate because centrifugal means it's going to give some centrifugal force to your material. Then upon using this kind of force, we can get some nano or micro form of fibers. So you can collect them, and then you can form some devices based on that. And then the other one is blow spinning. Blow spinning with the help of compressed air, we can pass the polymeric solution and then spray them using some voltage. Then we can form the nanofiber structure. And the other one is laser assisted melt blowing. We'll use the laser to heat the membrane and then polymer. Then we can form this kind of nano-woven structures like this. And the other one is microfluidic chips. We can form some core shell structures, one side and the other side. So two materials can be mixed and it can extrude in this way with the help of the voltage. Then the collector can collect all the fibers. Then it's easy to make the fibers this way. So yeah, here I want to introduce different kind of fibers, because whatever I said in the past, it was just like uniaxial or core shell, right? Here there are different forms you can see, like this coated structure, composite structure, neat structure, bistrawl structure. Here you can see how they bistrawl. It's like just drop cast your film and then you scroll them, then you will end up like this kind of structures. And then wet spinning structures. Here you can see they use some rotating coagulation bath. Like if you are going to prepare some fibers, you just put your polymers plus some functional materials like mxine, and then you extrude them into the water bath or some anticoagulation bath like that. Then you can collect them with the help of spool. Then it's very easy to fabricate, right? So yeah, there are many different variables in the current scenario. Variable 1.0, we are able to see smart glass, smart band, smart watch, and in the future you can see this kind of invisible conformal skin adorable devices like this, or soft wearable devices, and tattoo based devices. So it's good. So yeah, we'll expect more. And then yeah, here you can see the basic structure, how the electrospinning work, because I said I work on fiber structures. So now I primarily focus on this method, and this is the very basic setup. You can see we just use some pump to pump the polymeric solution. We fill the polymeric solution here, and using the pump, using the high voltage, we can collect the fibers here with the help of collectors. And then if you want to tune your fiber morphology, you can also tune by using some different solvents or some parameters like tuning your flow rate or voltage. All these kind of things can be done. And if you can tune your needle system from uniaxial, this is like one needle. If you have double needle core shell structure, here you can visualize it, right? Here you can see the core solutions from here, and the sheet solution is coming from here. Then you'll end up with the core shell structures. So there are different methods. If you can tune all this, you can end up with a different interesting morphologies. So this is another, in this article, they have mentioned what are all the different ways to collect, and what type of fiber system they can form using different setup. They can change the components and they can end up with the different structures. So yeah. And this is another article we published recently. And here we talk about polymeric system, conjugated copolymer system based electrospun nanofibers, and then use them on different fields like sensing, different kind of parameters. This is open access, anyone can access, anyone can read at any time. So yeah, you can have a look on it. And this is another paper we published. This one is for sensing pH and temperature and metal ions, these kind of things. And we also discuss about electrospinning in this review article. Yeah. And then, here you can see electrospinning have a lot of advantage. It has very good applications in different fields, starting from smart textiles, smart garments, optoelectronics, energy harvesting, batteries, food packaging, anti-fouling, biomedicals, and sensors. There are many varieties. And here I want to stress there are many different sensors, not only one type. So I can introduce few types, if possible, if time permits. Piezoresistive and capacitive, optical, piezoelectrics, triboelectrics, and magnetoelastic. So let's go into piezoresistive, because piezoresistive is very simple. Anyone can understand. For example, I already introduced, if you're going to apply some stress on your elastic conductive material, then if you're going to strain your material, then what will happen? Your strain will create the breakage of your percolation system. So that here you can easily visualize. See, if you are going to apply the stress to this material, okay, here you can see the charge is like this. It's moving very lithogous like this. But if you have another conductive material apart from here, they are using RGO, reduced graphene oxide, plus silver nanowires. If you have bicomponent RGO plus silver nanowires, you will have very good established networks like this. So you will end up with very good conductive networks, right? So if you're going to apply the force, or if you want to check your stress strain, then it's very easy to monitor those things. And the other one is, here you can visualize, they are using porous structures, and upon small deformation, the distance between these two electrodes and the dielectric material will be like this. And if you're going to apply more stress to your material, then the electron flow will be more, so that you will be ending up with the better currents. So if you can track the current or resistance, then you can easily monitor the pressure values. So yeah, here this is, you can imagine this is your human skin, and it's having many blood vessels, right? So if your pulse rate, if you want to monitor your pulse rate, and if you want to apply some pressure, you can see how it works. Here you can see the real-time image. They are showing how the breathable fabric they are using to monitor current changes like this, because this is going to establish the conductive networks between this, right? So if you are going to apply the pressure, it will create the networks. So it will give the electron flow. So the current will change. So upon applying different kind of pressures, you will end up with the different extent of your responses, peak responses. The same way here you can see they are using wearable smart textiles. Here they are using press, stretch, under bending. What will happen? They are measuring the delta R by R naught, the resistance upon different newtons, 0 to 5. They are showing this kind. Here you can see how it works, and the resisting value upon different newtons, ranging from 0.003 newtons to 3 newtons. So it's very easy working principle, so anyone can easily understand. Now, here they are using leather materials, because leather is also a form of wearable devices, right? You can easily make them, functionalize them using some conductive materials. Here leather have two different layers. One is top layer, can be called as corium, and the bottom layer is your grain side. Grain side is like very porous. Here you can visualize them. Yeah, here you can see here there are many fibrous networks, and if you are going to use some conductive materials, for example, if you are going to spray coat or using some drop casting method, you will end up with some conductive structures. Upon 0 kPa, there is no lighting, because there is no establishment. Here you can see the figure without pressure, the networks are not connected. If you are going to apply the pressure, the networks are getting established. So you will end up with a good current. So depending on the current range, you can monitor your pressure range. So 2.5 kPa and 5 kPa, 12.5 kPa. So you'll get with a different kind of pressure, you will end up with a different current responses. So you can monitor your pulse rate or finger motion, or if you want to get the speech recognition, then it can be done very easily using this kind of sensors. And then now here you can see, because this looks like yeah, this is microstructure. They make some structure like microdome, micro pyramids, and micro pillars, and they want to know which structure can be optimized and which is going to give the better results. So they are comparing with the conventional planar structure. If you have this kind of dome structure or pyramid structure, you will end up with the better stress concentration. If your stress concentration is high, means you will get better sensitivity. That is the idea. So Here they are calculating using some simulation softwares. Here you can visualize it upon 10 kPa, what happens in terms of microdome, micropyramid, and micropillars. So micropyramid is getting very here, yeah, from the simulation results, it looks like this one is giving better. So here you can see upon without pressure, there is no connection between the conductive structures. Upon under pressures, it's going to tunnel the current. The electron is going to be transformed from top to bottom. So that kind of stress or pressure can be easily monitored using this kind of structures. Then now moving from the resistive type of sensors, now I want to introduce capacitive sensors. Capacitive sensors, like here, we know that capacitance can be measured using this formula. And then, yeah, now how to measure the sensitivity? If you want to measure your pressure upon your device, then if your capacitance is getting changed with respect to your delta P, then you can monitor your sensing activity, like sensitivity. Here, now they are showing there are different ways to fabricate the devices. Here you can see they are using some electrospinning or bed spinning methods to form 1D structures like this. And then upon stress, pressure, you will end up with this kind of, yeah, configurational changes. So that will be easily monitored with the help of your eye or resistance or current. So the other way is to prepare some porous layers using some commercial foams or some salt, that kind of fillers you can add, and you can etch them and you will end up with some microstructures like that. Or you can use some sandpapers like emery paper we use in our homes. So that is very rough, we know that. And then we can form that as template and then use some conductive materials over it. And then we can also form the pressure sensors in that way. So there are many different ways to do. So now, yeah, here in this paper, you can see the difference among planar structure. This is conventional flat structure. If you are going to modify with some electrospun nanofiber structures like this, with some core shell structure, here you can see the TPU, and in the middle, it's made of silver nanowires. So if you are going to apply the pressure, how the variation will be. They are showing the 3D dielectric layers and the flat layer. You can see the delta C by C naught. The capacitance will be higher in case of 3D dielectric structure. So tuning the engineering the structures, microstructures or nanostructures will end up with a very good sensitivity. So that is the idea. So now this is basics. You can go through how the porous dielectrics are made. And yeah, now I want to introduce self-powered wearable sensors, because we know that triboelectrics, because it works on this triboelectric series. There are different materials, they rank them like positive and negative. So if you can use them as dielectric one, for example, this one, if you're taking negative material, you should take the more negative one. And the dielectric 2, if you're going to choose, you should take more positive one. Then the potential difference is too high, then you will end up with a very good energy generation. So this is the common criteria everyone should know. And the distance between this, the air separation should be tuned so that you will be getting very good results. So yeah, how when the top plate is pressed and two triboelectric materials contact, electron transfer from the positive material to the negative material. Like here, you can see the schematic is shown. And then once the load is removed, the two plates are separated and an electric potential difference is established between the two plates. The electric potential difference works as a driving force of the electron flow, for the electron flow from negative plate to the positive plate. So that is nothing but your current. This is how your self-powered wearable sensors work. So self-powered triboelectric wearable sensors work on this principle. You need two dielectric materials and electrodes to form this kind of wearable sensors, self-powered wearable sensors. And then this is another article we recently published. It's a review. Here you can see I explained all the sensory mechanism here. You can go into the details if you are interested. This is also open access, anyone can access. And this is another paper. Here I'm going to highlight the importance of some bio-inspired structures. Here you can see they are forming worm-like structures by using some stretch pre-strain strategies. Here you can see they are using pre-stretching and then using some graphene PU inks, and then they release, then it will form some wrinkle structures like this, and it looks like a worm structure. So they are showing like bio-inspired structures like this. They can form some conductive structures and it can work. It can light the LEDs like this. And the other one is epidermis inspired. You can see because our skin have dermis and epidermis layer. Epidermis is the topmost layer and dermis layer is the bottom. So how we can mimic this kind of structures by using some sandpaper and then drop some elastomers like PDMS and then peel, you'll end up with this kind of rough structures, and then do some electrode assembly, and upon stress, what will happen upon pressure, what is going to happen, this kind of rough structures is going to give better sensitivity. That is the idea. So they publish this kind of works. So yeah, so nature inspired micro nanostructures are quite interesting. And why we want this kind of nature inspired micro nanostructures? Because it's going to give exciting features like this, which is very important for the wearable aspects. Because if you're going to use on your body, it should be easily adherable and it should be very conformable. So it won't get easily come out of your body, or yeah, so you need a very good attachment with your body. So that is more important, and it should be tactile, and it should have very good interface. And then yeah, so these are all the things we should take care. So how we can do those things? By tuning our micro nanostructures. So yeah, here you can see they are mimicking like a root inspired structure, because here we are going to form some elastic polymer plus some metal filling. How they can form this kind of metal film, how to enhance their durability by forming some interpenetrating root inspired structures like that. And then for biomedical application, for stretchable electronics, so many of the things only rely on the structural engineering. So structural engineering is more important for the real-time applications. So here you can see they are using this kind of 2D material. Here you are able to see, and they are forming this kind of nature inspired nacre structures, bio inspired nacre structures. Brick and mortar looks like that. Here you can see, you can compare this and that. Here you can see there are many layers like this, and yeah, upon stress what will happen and how they delaminate. Here you can see, yeah, upon stress what is going to happen, how they fracture, and how they tune the strength properties of this kind of, yeah, here I say, because the electrical conductivity for the electrodes is more important, as well as their mechanical strength, the tensile strength. So they are able to balance this with yeah, in this work they are able to balance this. When compared to other works, it's quite better. So this kind of nature inspired structures are quite important for the good device performance. And the other one, here you can see leaf inspired structures. They are able to form this kind of, because leaf have many substructures. You can see if you fine tune, or if you are able to see under the sunlight, you are able to see this kind of structures. One has a vein and the lamellar structure. So here we can compare them with our functional materials like this, because I already say this is emexine, and this emexine is like a sheet. So it can be considered as a lamellar, and the other one, silver nanowire, is your like a vein. So this kind of structures can improve your strength, and it is also giving very good shielding effects. So it can be helpful for your electromagnetic interference shielding. So they also studied this kind of things by optimizing the emexine content. So it is very important. Understanding the structure and studying their structure and optimizing the structure and optimizing the fillers, these kind of things are quite important for the wearable sensors. And here you can see the nature inspired structures. How the cockroach can sense. They can sense in the dark room, how they can sense by their antenna. So the same way our triboelectrics, or this kind of, yeah, here you can see how they fabricate the device. Like here, they are using copper plus polyamide fibers just by tailoring them, and then they cut and they can stand up like this. So here you can see electronic component on the base, and the top it has polyamide structures plus silver PTFE. So here one is going to act as a positive and the negative structures. So yeah, if our human skin is going to yeah, because our human skin have positive charges, and this kind of antenna is going to have a positive charge. So this kind of charge discharge, electrostatic induction, we know that when we are using our comb, how the hair will move, right? Yeah, if you are using our comb due to electrostatic induction, that kind of the same mechanism, how it works, and how they can use this kind of techniques for sensing your proximity. For example, if you are nearby or how long you are. So the distance can be easily calculated using this VOC, open circuit voltage. So if your distance is too long, the voltage will be less. If you're getting very close and if you touch, the voltage will get high. And depending on their different angles, distance and angle, you will be ending up with a different voltage response. So this kind of cell power devices are quite interesting. So yeah, now, other one I want to share is they can also sense the wind direction. They can make human skin inspired structure like this. Here you can see mechanical responsive units and how they make. They just use some PET. PET is nothing but our Coke bottles, PET bottles, polyethylene terephthalate. They use that kind of substrate, and then they put some PDMS, commercial PDMS elastomer, and then they use some silica nanowires. Silica nanowires you can just put on the top and then use the conductive substrate to hold them, and then yeah, you try to monitor the resistance change, because we know that the electrical resistance of suspended silica nanowires, here this is nothing but your nanowire, and then your resistance is like 10 to the power 5 ohms. So now if you are going to pass the wind towards this direction, then it will move, right? So this kind of wind speed can create the resistance change. That kind of resistance change can be easily monitored. So with the help of this kind of one-dimensional silica nanowire based sensors, we can easily monitor the wind speed like this. So yeah. And the other one is they are using some CNT, carbon nanotubes. This kind of conductive fillers they use to make three different layers. One is like a very sparse, very thin, and the other one is medium structure and the dense structure. And they also optimize the conditions like this, and then they monitor their sensitivity. Before I explained with the help of silicon nanowires, in this case they change into different conductive material called carbon nanotubes. This is also like 1D structure and it's very, very small. So here we can see the difference among a different density. For example, this one is very less and this is medium and then this is dense. So if you have medium structure, you are able to end up with a very good sensitivity. So they are demonstrating this kind, and here you can see upon gas of it's going to like this. So this kind of variations can be monitored, and this is going to help you to monitor your wind speed, all these kind of things you can do. And here, this is another example for bio-inspired self-powered flexible magnetoelectric sensors. Here, it is going to be, here you can see they are using different structure. One is before and after compression, what happens. Here they are using magnetic pillars, like they use some elastomer, commercial elastomer called EcoFlex, then magnetic filler is this one, and then they use the circuit here. Then when we are going to apply some stress on it, what will happen? You can see the differences. They are using some softwares to calculate the simulation software to study the stress, one way stress. So here you can see upon increasing the different magnetic powder content, what happens, your voltage generation is getting high. And if you can tune this kind of structure, here you can see this is like flat, both the sides on top and bottom it's same. But if you tune this to 6, 4 and 0 like hemisphere, then your performance is going to get enhanced. So this kind of magnetic flux is the change in magnetic flux is important. So if you can optimize your structure like this, the change in magnetic flux can be achieved very well in case of hemisphere. So with the help of fine tuning your microstructures, we are able to get very good results in terms of electricity generation. And now I want to introduce this kind of pattern structure. Here I'm going to introduce about electrospinning plus pre-straining strategy to form this kind of wrinkled structure, plus having some nano ridges like this. So how we make this kind of structure? First, we start up with our electrospinning method to form 1D structures like this, and then we use some PDMS elastomer, and then we anneal to cure the elastomer. Then you can peel them, and then you can see here there are many fibers getting embedded into your elastomer like this. And then if you can wash, because we know that here we use some water soluble polymer, then we can easily etch them. So you'll end up with some nano ridges. You'll be having many values like this. And then we use some pre-straining methods, and then we use conventional method to prepare some silver conducting layers over our material like this. So finally we'll get micro and nano structures, yeah, like this, so in one substrate. So here, this is the SEM evidences for this process. I said how we do this and then how we etch this. So in the initial case, we just embed the fibers like this with the different timings to form different dense nanofibers like this. So now we, yeah, peel them, and then here we can see few nanofibers on the surface. The others are getting embedded, so that will give rise to good mechanical properties as well. And then we etch them, so we will be ending up with this kind of nano ridges. So here the evidence plus SEM plus AFM, you can see the 3D structure. There are many crevices like this here, you can see. And after forming silver nanoparticles, we are able to get this kind of structure, which is quite similar to our human skin. So I just can say it as skin inspired micro nanostructures. So yeah, now we also try to characterize the silver nanoparticle formation by using some FTIR characterization. And then we study the surface energy, because surface energy is quite important for the good substrate formation, good conductive substrate formation. So using the flat substrate, we are not able to get a very good surface energy. But if we can tune these structures, and we are able to get double the surface energy. So yeah, we can end up with a very good crystalline PPPDMS silver nanowires, silver nanoparticles. And here we check the transparency versus sheet resistance for the different substrates. Here we are comparing flat. FPDMS is nothing but flat, and using pattern PDMS with a different timing to form the silver nanoparticles on it, like 5 and 30 seconds. Using pattern PDMS like micro nanostructured PP, that is nothing but your PPPDMS. Within 30 seconds, we are able to get very good conductive substrate. Yeah, here you can see the differences among two different structures. Here I'm comparing the stretch cycles. We do the cycles for, yeah, the two different substrates. One is FPDMS, the other one is PPPDMS. Here we are able to see which is having very good durability, nearly 10,000 cycles. It's very robust. It's retaining its conductivity. And why this kind of good durability, we are able to achieve very good stability in terms of wearability, because we have this kind of microstructures. So yeah, in the conventional state, you can see the stress is concentrated more, whereas in terms of micro nanostructures, we are able to dissipate the energy. So we are able to make the stress distributed over the surface. So that is more important to get the very good durable wearable devices. So here I'd like to share the differences between PPDMS and PTMS and FPDMS. So here we can certainly see the differences in the recovery ratio and the residual strain. So if the recovery ratio is high, means your device can work longer. So that is quite good. And the other one, I want to share the current durability. Here you can see current versus different strain percentages. We do it for 0, 10, 20, like this kind. We keep straining the device conductive electrodes like this, and then we monitor the IV curve like this. And then we also check the sheet resistance over different tensile strain and bending cycles. Yeah, it's quite good. And here we can see the strain studies for 5, 10, 15, 20, what happens up to 2000 cycle we did. And then residual strain and recovery studies. And then we also check the antibacterial test for the common bacteria like E. coli and the Staphylococcus aureus. And we also check the saline solution immersion stability, because because the working environment can be of anything, not only like water or something. So we also want to check saline solution. So this is another one to check the sensory response in the finger, muscle motions from the forearm like this, and then when you're going to speak with a different modulation, what will happen? For example, yes, no, if you're going to speak loud or mild or normal, then the peak intensity will be varying. So with the help of that, we can easily track what mood you are in. So yeah, it is quite important. Apart from that, we also do some strain insensitive pressure sensing, because we are going to use it in our body, so it will have some interference. For example, I already say, if you're going to strain or if you are going to do some workout, so that time your conductivity will change automatically, right? So how to avoid that kind of interference when you're going to monitor your pressure by using this kind of PPPDMS structures. So yeah, we do those studies, and we also checked up to 30% the sensitivity retained, so which is having very good yeah, performances over wearable conditions. And this is another proof of concept demonstration we did with the optoelectronic devices using PPPDMS with the conventional ACL device, and the other one is for organic LEDs like this, and we monitor. And the other one is just to mention, this is like another triboelectric series I already introduced, and here I already say the farther we have, then we'll have a better energy generation. So yeah, you can go through these things. And this is the example, real-time example. You can see how they fabricate this kind of TENG structure using some natural-based materials. Yeah, so yeah, we can also try this kind of structures. It is possible to do with. So yeah, because we should know that the distance and the dielectric properties of the two dielectric materials is quite important, and the maintenance of our surface charge density using microstructures. Like for example, here you can see they are able to tune, they are able to adapt rose petal structures. They use the rose petal templates, and then they form this kind of structures, and then they use it for the triboelectricity generation. Then yeah, it is giving very good performance. So in the same way, yeah, we are able to do some wearable devices, smart garments. Here, this paper we discuss about how we use some stretchable SBS polymers to make yeah, 3D structures of smart garments using some polymeric nanostructures. Here you can see we use two different PTFE and PU with the different ratios, and we optimize the conditions to get energy generation. Upon straining your textiles, then you can enhance your energy outputs, then you can store them in the capacitor, and then you can utilize them, harvest them after. The same way, we are also doing some piezoelectric generations, and here we are using perovskites with the conventional PVDF piezoelectric polymer, because we know that piezoelectric polymer have some different phases, and it is quite important to have a beta phase, because which is having very good ferroelectric property. So yeah, if we can tune that phase by using some fillers, like here we are using some perovskite quantum dots, and then using this kind of quantum dots, here you can see this one is your quantum dot, and we have some CNC to give some stability, because in the beginning I said that perovskite have very limited stability. To improve the stability, we have to tune the structures and have to use some ligands to protect the QDs. So we do those things, and then we employ them in the nanofibers, and we check the, sorry, excuse me. So yeah, we use them, and then we harvest the energy using this kind of system. And we employ them to check different body motions. Yeah, so you can look. And here, this is another paper. In this, we designed two different kind of structures. One is this, we can shortly term this a muscle fiber inspired structure. It looks quite similar to our muscle fibers. And here, how we prepare this kind of structures is given here. We use electrospinning, and then yeah, we are able to form electrospun reinforced nanofibers, and then we use some silver nanoparticles. And here you can see how the nanofibers look like. It's in a microstructure, and then the nanoparticles are visible here within like 100 nanometers maximum. So average is like 60, 70 nanometers. And then yeah, we confirm the presence using some EDX, and we studied the functionality and crystallinity patterns, and yeah, thermal stability. And then we use them on wearable gloves like this. So if we are going to make some motions which using yeah, this kind of resistive structures, we can tune, we can able to monitor what the one who is going to make sign language, we can easily understand what is going to say. So yeah, with these kind of things we are able to do. And yeah, here we can see the tensile strength performance and its durability here. And yeah, we also studied bend cycles, stress cycles, and we do some FEM analysis and ANSYS. Here we can see the stress distribution in the normal uniaxial structure like this, whereas ERCF, electrospun reinforced conductive structures, have very good stress distribution like this. So yeah, we are having very good results in this in terms of durability as well as the chemical stability. So yeah, finally we formed the device to compare the two different structure. One is like uniaxial, other one is electrospun reinforced structures, to form piezoelectric nanogenerators, and then we check the durability over time. And we also tried to check the forward and reverse connection to check the piezoelectric mechanism is valid or not. So in comparison to the conventional WSNG structure, ESNG is giving more better results, nearly 4 times better results we got. So yeah, which is having very good durability in terms of air blowing also, because the fiber structures are very finer. So you might have felt that it is very easy to wash off or something. So because of the nanofiber interaction between these things, so which is having very good surface area and which is having very good adherability, we check the air blow structures which is available in the paper. If you have any doubts, you can go through this. And finally, I want to say, because we use this kind of sensors, and the major thing is we are able to monitor these many things using like sugar, temperature level, asthma, HR, motion, BP, and what are all the things we have to be careful about our human body. So how it is working, the motion sensor, the sensing is the primary thing. And then using this kind of 60 techniques or wearable body area networks, we are able to convert this kind of electrical signals and then transform them using the internet to we can get the remote health services from the medical practitioners like this. So, but yeah, this is good, but they have some safety issues, because whatever we have, the privacy, because all the details, our body health details can be tracked by someone. So it's quite important to have very good safety platforms. And yeah, we have to be very careful about our details. So yeah, the major thing is the security. So people are working on it. I expect they'll be coming up with the good results this. And these are all the papers I published in the recent few years. So if you are interested, you can go through. And for this presentation, I referred this kind of articles. Yeah, you can also check. And yeah, this is my social media platforms. I'm available on Google Scholar, ResearchGate, and LinkedIn, Orchid. If you have any doubts, or if you are interested in doing some collaboration, we can speak about. And yeah, I want to share some pictures which I got in Taiwan, which is yeah, newly we take inside the Taipei city. So it's a rainy day, so we got some clicks here. And this is some traditional yeah, celebration in the temple near Taipei main station. And this one is in the Yangshan National Scenic Area. This is a national park, Yangshan National Park. Very good view. It's very tall mountain. And this is another place we recently visited called Sitao. It's in the central Taiwan, yeah, which has very old cypress trees, which is nearly like more than 1,000-year-old trees are available there. Yeah, so if you are interested to visit Taiwan, I welcome you all. You can explore Taiwan in future. And then this is my professor, and these are all my teammates, and I want to thank them in this time. Yeah, without their guidance and their support, I cannot achieve all this. So I want to thank them all in this time. And then I want to introduce our NTUT website. This is a NTUT website. And if you want some information related to the scholarship, you can go through this link. And this is my department. And these are all the collaborators I have. I want to thank them because they give their ideas and views, and they are very patient and listening to me, and I always suggest many ideas, and they also give their outputs and inputs. So it's quite good. Yeah, we have a very healthy relationship here. So I want to thank them all. And I want to finally thank the organizers, especially Kiran sir, thank you very much for giving me this opportunity. And I welcome the comments and queries from the audience. I thank you again. Thanks. Thank you, everyone. Thank you.
Dr. Loganathan, thank you very much.
Yes.
Like,
thank you, Professor.
After seeing your presentation, I have a few queries that we can discuss. Like, now, what is the difference between the education that we have seen in India and Taiwan? Is there any difference? And how for now our students and the faculty members who wish to do PDF there in Taiwan university, because many universities are there.
Yeah. There are many options available. First, we have to contact the PI, project investigator, if you want to enroll for postdoc or PhD. Yeah, the major difference I feel is, because the education system here, I feel they don't work too much. They don't do many hard work. They do smart work. Yeah, they don't focus more on their education. They enjoy as well. They also do many other activities. They don't have boundaries between men and women. For example, boys and girls, they are not always separate. This is like real co-education, I feel. Here they don't have any boundaries in front of professor. They are very gradual. They don't act like, oh, you are you are no one, you are not my classmate or something. They have their own idea and they are able to speak. They are okay to speak with the professors. But in India, we have some little boundary. I feel it's not easy to communicate with professors. Yeah,
There
here we have more freedom to
we
talk.
call it as a golden distance. We don't know how much the professor knows also. That problem is also there. And I have a small query, sir, in the terms of sensors.
Yes.
Are you involved in generating new sensors, or are using the existing sensors you are doing the research?
Oh, sorry. Yeah, we do sensors, and in the recent years we are working on some self-powered sensors like piezoelectric sensors, but the mechanism is same. We try to optimize the condition, we change the structures, and we form different morphologies.
Can we, sir, my just a question is like, can we have a sensor which can measure the quality of water?
Yes, that is possible. Yeah, there are few sensors I read in the before, but because the measurement is quite difficult, underwater sensing is little different. Yeah, it's not easy like what we are thinking. Yeah, we should have that facilities too.
This college where it is located, it is famous for this aquaculture. And when we talk about aquaculture, people are concerned about what is the quality of water, what was the quality inside the pond and outside the pond, because they cultivate fish and prawns more in this area. So do we have any sensors which can help the farmers to have this quality of water check?
Yeah, I think we can do, but we in the past in my group itself, they are working on some metal ion sensings from the sources like water sources. They do, but you mean you want to check in depth and you want to see in the different water elevation levels. So I don't know how to collect the samples, and it's yeah.
Even when we meet the farmers the last week, they also said they are bothered about they're concerned about the quality of soil also. Like they asked us to give some IoT devices so that they can measure the quality of water, quality of sand, something like that they're asking. So obviously I'm just querying you, like, can we design sensors for this type of requirements?
Yeah, that is possible. But at present, we are just focusing on some wearable, this kind of
wearable technology.
Yeah. And there is much demand for this kind of wearable sensors in recent years. So yeah, we switch because in the past we always focus on some wearable optoelectronic devices. We don't do much sensing. Yeah, because of the societal changes, we have to adapt. Yeah, we have to fine tune our research, and we need some changes. So we switched gradually. Yeah. And some of my juniors also working on similar field, and they don't do water research. Before they do in 2015, 17, in that range, we published several articles like colorimetric sensors, optical sensors.
What
We
was
also
more
published.
interesting is like the correlation between the sensors and IoT, because most of the people now they are aspiring for different type of IoT devices. And like I said, no, there are many societal applications which force us to go for this IoT and sensors, particularly in aquaculture and related societal applications. And as far as the presentation is concerned, it is wonderful. And I request all the participants, if somebody wish to interact with our professor, they can unmute themselves and just interact, please.
Yes, thank you, thank you. Thanks for your valuable inputs. And yeah, if I find some solution, yeah, definitely I'll have.
Definitely, sir, because it is now we are not going for a pure research. It is only interdisciplinary research that is happening with focus on societal applications. So we need a lot of discussions and brainstorming sessions like this, so that we can come for a solution for a particular problem, because problems are real time problems. And you said to collect data is a big hurdle when we're starting this particular project, something like that, because the real time data sets we need, and then only our research is usable. Because whatever research we do, if it is theoretical and if nobody is using it, this research does not have any significance.
Yeah, we need some direct impact. I also feel, yeah, because
yes.
in the past, what we, they do many fundamental research, yeah, but in the real time, it's not going to be that useful. One which is having direct influence and direct applications to the human society, it's good. Yeah,
that is the reason yesterday we have a session by Dr. Kali Charan Rath where he integrated this robotics and machine learning and cyber security. Because all this, see, he belongs to mechanical department, is working in machine learning and robotics now. So all are interdisciplinary research that is happening in and around. That is the reason we need to discuss, and we need to collaborate and have a solution for a societal problem. That's what my interest is. For all the participants, I request, if you have any queries, please unmute yourself and you can interact with our professor, or we can conclude this session.
Some of the participants are raising the hands. If you have any doubts, you can ask our research
Farah
professor.
Nazam, if you wish to interact, you can unmute yourself, sir. Dr. Priyanka.
Samrajyam.
Dr. Samrajyam, if you wish to interact, please. I think Loganathan garu, we can conclude the session. Because they are very clear with the presentation. Presentation is very clear. I think it has taken more time for you to prepare all the slides.
Yeah. Many efforts have to be paid,
yes,
and
yes.
It's not like 1 or 2 days. I'm reading for the past few years. I used to collect and read more. Every day we have to update. It's not like just reading 2 days and doing the research. Yeah, when doing the research, major thing is to do some literature survey, find the research gap which will work and which will not. So yeah, we have to update ourselves. Have to spend more time on reading the literatures. That's quite important.
Dr. Prasad garu, we can conclude, sir, please.
Okay, sir. Very useful session, sir. Sir, we are open the minds of researchers and put the seeds in their heads. So definitely it's very useful for so many young and budding researchers. Actually, up to now, we are thinking wearable technologies, smart watches, smart spectacles like that. We are not thinking about the smart textiles. We are introducing that one, and we are show your expertise research on this one. Really appreciate your efforts, sir. How many years we are working on this one, we don't know, but you have a very good research which are useful for future generations, sir. So thank you very much, Loganathan, sir. We have the long association with our college. If you are visit the India, please come to our campus. Please talk with our researchers and talk with our budding students offline, physical mode, sir. It's our college invitation, sir.
Oh, sure, sure. Yeah, yeah. I always receive this kind of yeah. I welcome all the suggestions, and I always want to interact with the people. Yeah, I want their inputs. Yeah, everyone have to discuss, and it's yeah. It's not like one people have to talk, other people have to listen. Everyone can share their thoughts. It's quite important for the research. Yeah, yeah. I
Yes, sir.
believe, yeah, if I come to India, I should definitely, yeah, visit all the colleges possible. Yeah, because
If we
here
were,
it's quite
if we are,
hectic
if we are
situation.
visiting the India, please inform to our HOD sir. Our HOD sir will take care of everything, sir. No issue, sir.
Yes, yes. Thank you. Thank you. Thank you.
So thank
Yeah.
you very
Thanks
much,
for
sir,
your time.
Loganathan, sir.
Yes, yes,
Dr.
yes. Thank you.
Loganathan,
Yeah.
have a nice day, sir.
Yeah.
It's really wonderful to see you online. Thank you very much.
So,
Thank you, sir.
dear,
Thank you, sir. See you, sir.
dear participants, this is the time to end up our